G'day, my name is Brennan Gregg. I'm a performance expert at Oracle, and today I'm joined here with Rock. I'd like to give an informal talk on the art of performance experimentation. This is something that a lot of people don't do, and they're really missing out on a useful skill that you can learn for tackling complicated performance issues. So, what I'm talking about is, and I've just drawn up some talking points here, this is an informal talk. When people are analysing performance issues, a lot of people will do a lot of observation. They'll be looking at statistic tools, maybe tracing tools such as dtrace, and looking at the data and trying to make sense of it, trying to infer system behaviour
from their very complex initial environment.
From their complex initial environments, that's right. And when you point to, especially dtrace, which can see everything, you point that at your ridiculously complicated environment, it's confusing, you can get lost, you don't know where to start. You have all this data that you're trying to pick through. So people like myself and Rock, we actually figure out a lot of performance problems, not because we're super good at the art of inference, we're okay at it, we are pretty good at it, but we also have another skill that we use quite a lot, and that's performing small experiments so that we can learn various things about a system. And in fact, I would say it's of equal importance in my day-to-day job. I do so much experimentation as well as observation. So it's really two things that you want to get good at if you want to become a performance expert. The reasons we do experimentation, and when I say experimentation, I mean you run a little program that applies a certain load and then you examine how that behaves. The reasons why you do that, to confirm issues. For example, someone says, this network interface, I've got a problem with my network interface, and even though it's 1 gigabit Ethernet, it can't drive at 1 gigabit Ethernet. I'm capping out at 40 megs a second. Okay, well, there's lots of network benchmark tools out there. The first thing you should do is grab something like TTCP, Test TCP, or UPerf, or iPerf, and just check whether the network interface can run at full speed. And that's standard. Like if you're troubleshooting network problems, it's pretty standard to run a benchmark, just to have a data point.
Get on the map, right?
Get on the map, that's right. One of the key advantages of that is it's isolating components. So if you're testing the network interface as part of a large complex system, there's all sorts of other factors at play. By just isolating out the network and performing your test, you can put it on the map, you can tick that off as either a problem that you don't need to keep, a problem that you do need to look at and investigate, or as a known to be working component, so you can then move on to the other areas. So yeah, to confirm issues, and I use networking as an example. Another example might be disk I/O. You think you've got a problem with a disk. How fast can it read? Can you apply a read workload to the disk?
And you need your test, right? The test little applications that you might be using, you need to make them very flexible. You can, you're diagnosing a performance problem, which might be, I'm going at that speed, whatever. You're doing an experiment, and then you find out that, well, it depends a lot on the write size that you're using. Or as you cross that boundary, you see that something has clicked, right? And so, you're trying to confirm somebody else's problem. Not everything is always the same everywhere. But if you can be flexible about what you are testing, then that's when you're going to hit the clicking point. Just this week, somebody was telling me there's a problem. He was testing, couldn't reproduce. Well, it was 128K. The problem only showed when you did 32K I/O. So, you're mapping stuff, and then basically start with something that is very different, is what I tried, and then try to hone in on the differences.
That's a good point. And I guess part of it is with performance, both of us assume nothing about the system. We test everything. That's another reason why people may not do much experimentation is, well, they assume that it's not going to be the network that's the problem. It's not going to be the disk that's the problem. Maybe it's the application. Maybe it's Java, and they're thinking there might be a problem with Java. Don't assume anything that you haven't tested and you haven't measured. And for a lot of this stuff, it's easy to create a small little test program so that you can inject that workload on that component, check that it works fine, and then move on to the next one. So for confirming issues, isolating components to make your job easier so you're not tackling some huge complicated environment. And we also do experimentation to learn performance analysis tools. So I've taught a lot of dtrace classes, and customers, I understand the situation. You've got a performance problem, your manager's breathing down your neck, you want to solve it as quick as possible, and so you fire dtrace straight at your hugely complicated application, and you start drowning in data. You don't understand dtrace that well, and you're trying to learn dtrace at the same time as navigating through the internals of something very complicated. And so you're really crippling yourself and making it harder on yourself than it needs to be. Of course, it's ideal, and I know a lot of people don't have time for it, but I do write a lot of programs to exhibit a single issue. It might be a 20-line C program, so that it exhibits a single performance issue that I can then check with tools like dtrace.
Because a lot of stuff about performance measurement, and you were going about that, is when you are talking about one performance measurement to the field or to people, you really want to say, here's the performance and here is why. The why is almost more important than the number, right?
Yeah.
Don't put out performance information unless you really understand why, why is it that you're getting that number, and what are the components that are saturated in your environment.
Yep, that's right. Also about performance analysis tools, apart from, say, doing CPU load and then looking at a function, it may, if you're troubleshooting an application where a client logs in and then does some transactions, you might write a little experimentation program just to do a login. And analyzing that, rather than, say, analyzing the entire client environment, might make it a lot easier. You might write a little program just to do individual transactions of interest, but you've isolated them out. You've also written the program yourself, and the act of writing these experimentation tools does teach you a lot about performance, especially if you're stuck and you don't know where to start. If you learn how to write that, a lot of people don't know C, but if you learn enough so that you can write that simple program. I'm not asking you to write a huge application, I'm just asking you to write like a 20-line program or
and you write them in Perl, right? You can do a lot with Perl today.
You can actually do a lot with Perl, especially for networking. Perl makes it really easy and the libraries that come with Perl, look at the man page for Perl IPC, it's really fantastic. Especially if you're, say, troubleshooting a remote application that might be a web server. You want to do, say, maybe XML RPC calls to it. Perl's a great environment for that. Also LWP for libweb.perl, that lets you simulate a lot of web activity. So again, you could write little tools to perform that experiment.
When you're writing those tools, you're also, right, one of the very key things you're trying to do is get to the point where the system you're trying to understand is delivering you stable performance.
Yes.
Right, you're really trying to get everything that is variable about this, right, out of the way, so that you know you're measuring something that is of interest.
That's right.
And another point also is because of the way CPU, for today's complex architecture work with a lot of caching, you probably want to build into your tools writing the ability to do a perturbation. I kind of very often go into a cycle where I'm going to run something that I'm not interested in just to perturb everything, and then I'm going to run a targeted experiment that is, how does the system behave if there's been something else running on before? And then try to hone in on this. Different perturbation, different measure point.
Yep. And also measuring points not just from artificial perturbations, but also if you've generated some little experiment tools to, say, log in and do just the most basic customer query for an application server, you might cron tab that or schedule that to run every minute and generate a log file of latency. That's really useful information as well. When someone says, I had a performance issue, go back in time and look at the latency from your little experimentation tool. So a lot of these, there's a lot of value in doing that. And another point I wanted to make is if you do write that little tool to log into an application, do a few things, it's really going to teach you about the process. Just the act of running it. It's how do I log in? How do I do the credentials and authentication? Is that encrypted? Et cetera, et cetera. And it will give you a clear idea of the pseudocode for doing that transaction, and it gives you almost a checklist of things that you can then go and investigate. So the act of generating experimentation tools teaches you a lot about the thing you're trying to measure. So those are some of the reasons why we write experimentation tools. Some of the test tools that I write and Rock writes, I've got little fact, a lot of these are Perl programs to do random file and device I/O. In fact, I put some of them on my blog. And I use them all the time. If I want to see how random file or device I/O is processed, I can just apply that little Perl program. Same for sequential file or dev I/O. I found I don't really need to write these in C in terms of, sometimes I'm writing these load tools to investigate maximum performance. So it's not just how is that I/O processed, but I will run a flood of these tools to see what bottleneck I encounter first on a system. That can be another useful thing you can do with these types of tools. And in that case, sometimes it can be better for a programming language like C to compile it up. Perl actually does a reasonable job, especially if it's disk I/O or network latency. That's going to be the long pole in the equation. It's not going to be Perl.
You did get 500,000 IOPS with Perl?
That was I did do a performance result of 500,000 IOPS on a single Oracle Sun storage server. I did end up using C for that, but I did...
It was close, right?
It was close. I think the difference between C and Perl was 2.5%.
Okay.
So Perl actually took me...
It's pretty amazing.
Yeah, it is pretty amazing. Interpreted languages like that can have a bad rap, but actually put it to the test and see if it...
That's correct.
And putting it to the test is what this informal talk is about. If that's another classic performance problem. People criticize Perl, maybe they criticize Java or C.
Yeah.
Write a little program and test it out. Write a program that simulates what you're interested in, whether it's floating point arithmetic or web transactions or whatever, and put it to the test.
You know, when in the I/O world, which we're involved both, extensively, and I/O is an infinite amount of time. So there's a lot of CPU available to you. People worry about checksumming and stuff. This is something like I almost never see as a problem. So we have a lot of CPU between I/Os, and I/O is a different world.
Yep, that's for sure. Asynchronous and synchronous file I/O, that's just another example of tools I write. You'll hear, especially if you're doing file system work, you'll hear whether the application is opening up the files with the ODSync flag or OSync flag to do synchronous I/O, which a lot of databases do. That has a huge, that makes a difference of how the file system will process that I/O. If you're new to this, have some simple programs that when it calls the open, it uses the sync flag so that you can do your own sort of tests and get the hang of what that means to do synchronous writes. That's what we're usually talking about. CPU load. If you're examining how CPU is, how code is being executed across CPUs, you can write programs and keep running them to flood the CPUs to see how that works. Also, and this is the point about learning performance analysis tools. If, say, you've got a hot CPU problem, CPU is heavily utilized, and you're trying to use an analyzer or you're using dtrace or something like that to identify why the CPU is hot, you can get the hang of that by writing a simple program in the language that your application is in. Maybe that's Java, maybe it's C, maybe it's Perl. Write a simple program, the fewest lines possible, that calls one hot function, so that you have a known workload. Then practice pointing your analyzer at it or pointing dtrace at it to confirm that you can identify that. It's a really useful exercise to go through. Same deal for memory load. If you're doing a lot of mallocs, and I've analyzed a lot of applications that have malloc issues, how can you identify which stack trace is responsible for the allocs, whether things are getting freed or not, whether there's a memory leak in a program? So if you want to get good at identifying memory leaks which cause performance problems, write a simple C program that has a memory leak and
try to find it.
And try to find it. Make it easier for you. It's a learning exercise. And like I said, customers have these problems and they're trying to learn it on the fly with the huge complicated applications. So make it easy for yourself and write a little program that exhibits that issue and learn it from there first.
Yeah.
Another example would be locks. So lock contention can cause all sorts of problems, multi-threaded applications, maybe it's spin cycles or adaptive mutex. If you can, write some programs that exhibit known lock problems and use the tools in Solaris to identify them first, like lockstat and p-lockstat, which are dtrace based. So that's a quick informal talk on experimentation. It's something that Rock and I do a lot. That's how we're very good at performance, and I think it's of almost equal importance as observation when you get into analysing a lot of difficult issues. Think of what tools you can write to confirm issues. Like I said, a network issue, can it run at full speed? Isolating components, and also it helps you learn performance analysis tools. Thank you.